Hello everyone. We're starting a free open lecture in our Discord channel. All our lectures are indeed held every single day, without breaks. If you're a viewer and want to ask questions and get answers online, then join our lectures. You can find the link to Discord in our Telegram channel. To find out the time of the lecture, join our Telegram channel in Discord. Oh no, Ghost. 2 seconds, 256 megabytes. But again, not that interesting. The conditions, but still. In the best traditions, today we have 50 million ghosts. And for the meeting, we have prepared a lot of candles, each of which burns for exactly 3 seconds. In 1 second, our heroine can light 1 candle. More formally, we can spend 1 second to light 1 candle, after which it will burn for exactly 3 seconds and then go out. We won't be able to use it again. So, for each of the ghosts, we know that it will indeed arrive. In a certain number of seconds, precisely after midnight, and, at the same time, several ghosts can't actually arrive in the same exact second. Each visit lasts exactly 1 second. What is the minimum number of candles Anya needs to use so that during each visit, at least our candles are burning? Basically, in essence, Anya can start lighting a candle at any given whole number of seconds that are remaining until the stroke of midnight, including the moments just before midnight. Again, more formally, if we represent this somehow, we have a time segment. And these are the ghosts. We must prepare for them, well, here the problem says that R, but I am used to writing such coefficients as K. Actually, K candles should be burning at that moment. Well, as you can see, each candle burns for about 3 seconds. So, here we have a time period. We want to push the time periods as far apart as possible, so that they intersect with several ghosts. And at the same time, we want to make sure that in each of the segments, there are at least, well, more precisely, at each transition, there are at least K of our candles. So I decided to take K as 3. Speaking of which, K for me here is 3, and the candles, well, they burn for a certain amount of time. In this case, for example, abstractly, we only need to light 4 candles because this candle manages to burn just in time. This candle, for example, is lit exactly at the moment of the transition. This candle is just about to burn out at the moment of the transition, so it manages to last just in time. And we only need to relight just 1 candle, so to speak. Actually, the answer is 4. What are we going to do? How do we solve this? Actually, there are a lot of solutions here. We can probably solve this dynamically. We can probably solve this using flows because the constraints are very small. In our current setup, we have a total limit of 300. It is important to note that a candle can burn for 300 seconds, which means that there can be a total of 300 ghosts. And the number of lit candles should not exceed the maximum capacity of 300 in total, and also the moments in time. All of them, when they come, also have dreams. So, what can we do to solve it in the simplest way in our current situation and ensure it is effective and efficient? We can actually just use a priority queue. What exactly will we do for that? We'll go through all the times carefully and thoroughly, in detail and meticulously. These times are sorted here for us, but actually, if they weren't sorted, we could do the same thing, just sort them. Initially, again, we will sort 300 even with a bubble sort in that time. We have 2 seconds, so we have this very segment of arrival times. We'll take first time and, of course, we'll create a PQ. And let's see how many elements we have in our PQ. Well, of course, we have 0 elements at this point. So we need to throw K elements into it. We'll be adding them essentially in essence at this point in time, basically from this moment in time in a manner of speaking. In fact, so we'll be adding not the arrival time, but the departure time, actually. And we will definitely sort them in this priority queue from smallest to largest. Actually, let's say this is some time 3. And therefore we'll add time 3 plus, 2 plus, and 1 plus there. Then we'll move on to the next one because that's it. We've added 3. Everything matches, so we can move forward. We'll move on to the next one and check if this moment in time has already ended or not. Let's throw out the PQ everything that's less than this moment in time. Less than this moment in time, we ended up with 1 plus t. In this scenario, therefore, we simply decide to discard it, and then we find ourselves with the number 2. The number 2 is less than the number 3, so it becomes clear that we need to add 1 more. We add 1 more at this very particular moment in time. Precisely, again, plus t at our peak. And well, in the end, we'll just wrap it up here because we don't have any more behavior? Well, obviously, every time we throw a candle into the priority queue, we just add 1 to the answer. This is the variable that will count our answer. We will increase it. And also, for us, might definitely need to verify if we lit this candle at that time or not. If, for example, we have a lot of consecutive ones standing like this, well, and there the previous ones reached us, for example, we might end up lighting this one first, then we won't have enough for this one, and we try to light the same one again. So we'll just save in our set, for example, all the numbers, the moments in time when we lit them, so we don't end up lighting a candle twice. This can happen if we implement this in a very simple and straightforward manner, very naively, and without any sophistication, and that's it. This will be our answer. Basically, we read our number of ghosts, the time, and the number of things. We read all of this. If we have it, then it's time. The burn time of the candles is less than the number of candles we need to light. This is the only case where we simply can't just do that easily, so we introduce -1. In the other case, we create a priority queue and a set of our answers. Well, yeah, we won't need a counter if we just keep this set maintained. We can just throw in the size of our set. That's also an option. And then we just go through all of our, basically, ghosts. If we have PQMT, then we throw in, well, for now it's not empty. If our top element is less than or equal to our current ghost, that is, if the candle has burned out, then we let it go, and otherwise, we just stop. And then we add as many candles as we need if they're not already in the answer, of course. We do this in the other case, but we just choose a different moment in time. That's it.
Want to become a great programmer? Subscribe to our Telegram channel.